Hello everyone. Now we are starting the next part of the network layer protocols. Next topic is IPv6. IPv6 is the next generation internet protocol designed as the next step of IP version 4. IPv6 was designed to enable high performance and larger data space. This was achieved by overcoming the many of weaknesses of IPv4 protocol by adding several new features. First is improved header format. IPv6 uses an improved header format. In its header format, and options are separated from the base header. These options are inserted when needed between the base header and upper layer data. The routing process is simplified due to its modification. The speed of the routing process increases, the routing time is reduced. Second is larger address space. IPv6 has 128-bit address, which has 4 times wider in the bits in compared with the IPv4's 32-bit address space. So there is a larger increase in the address space. Address space of IPv6 is 2 raised to 128. New options. IPv6 has increased with functionality due to addition of entirely new options that are absent in IPv4. Next is more security. IPv6 includes the security in the basic specification. It includes the encryption of the packets, ESP, encapsulated security payload, and authentication of the sender packet AH, that is authentication header, for enhancing the security. Possible of extension. The design of IPv6 is done such a way that there is possibility of extension of protocol if required. Next is support to the resource allocation. To implement the better support for the real-time traffic such as video conference, IPv6 includes a flow label in the specification with a flow label mechanism. Routers can recognize to which end-to-end flow given to the packet belongs to. Next is plug and play. IPv6 includes plug and play in the standard specification. It therefore must be easier for the new users to connect their machines to the network. It would be done automatically. Next is clearer specification and optimization. IPv4 follows a good practice of IPv4 and omits the flaw or obstacles items in the IPv4. Next is IPv6 addresses. IPv6 address is 128-bit long. It consists of 16 bytes. IPv6 uses a special notation called as a hexadecimal colon notation. In this, total 128 bits are divided into 8 sections. Each one is of 16 bits or 2 bytes long. The 16 bit or 2 bytes in the binary correspond to the 4 hexadecimal digits of 4 bit each. Hence, the 128 bit in the hexadecimal form will have 8 into 4 is equal to 32 hexadecimal digits. These are grouped into the 4 digit as shown in the address. Every group is separated by the colon. IPv6 uses 128-bit address. Only about 15% addresses space is initially allocated. The remaining 85% being reserved for the future use. The unused address may use the future or expanding addresses space existing address types for totally new use. The IPv6 address in the hexadecimal format contains a 32 digit and it is very long, but in this address may hex digit are 0. We can take advantage of this shortening of the address by abbreviating it. A section is correspond for the 4 digit between any two colons. The leading zeros in the section can be omitted to reduce the length of the address. Note that only leading zeros can be dropped, but the trailing zeros cannot be dropped. This is due to abbreviation. The length of the address has been reduced to 24 hex digit. We can make the future further abbreviation if there is consecutive section in the consisting of only zeros. We can remove the zeros completely and replace them with the double colon. This further abbreviation has reduced the address length just to 13 hex digit. It is impossible to note the abbreviation can be done only once per the address. Also note that if there is 2 sets of 0 section, then only one of them can be abbreviated. IPv6 protocol allows a classless addressing and the CIDR notation as well. Next is categories of address. IPv6 defines three types of addresses: unicast address, anycast address, and multicast address. First is unicast. A unicast address is mean for the single computer as a destination. A packet sent to the unicast address is meant to be delivered to the computer specified by the address. Next is anycast address. This is the type of address which is used to define a group of computer which addresses which have a same prefix. A packet sent to an anycast address must be delivered to exactly one of the member of the group which is closest or the most easily accessible. Next is multicast address. A multicast address defines a group of computer which may or may not share the same prefix or may not connected to the same physical network. A packet sent to the multicast address is meant to be delivered to each member of the group. There is no broadcast address in IPv6 because multicast address can perform the same function. This type of address is determined by the leading group. All the multicast address starting with the FF or the 8 times 1s and all the addresses are the unicast address. Anycast addresses are assigned from the unicast address space. They do not differ synthetically from the unicast. Anycast addressing is rather new concept and there is not much experience about the widespread use of the anycast address. Therefore, some restrictions apply to the anycast address in IPv6 until more experience is gained. At anycast address may not use the source address in the IPv6 packet and anycast address types may not be assigned to the host but the routers only. Next is IPv6 packet format. The figure shows the IPv6 packet format. Each packet can be divided into two parts. First is base header and second is payload header. Payload header is extension header over here. Base header is mandatory part and payload is the optional here. Payload follows the base header. The payload is made up of two parts. First is an optional extension header and the upper layer. The base header is the 40 byte long, whereas the payload consists of the extension header and upper layer data can have information worth up to 65,535 bytes. So first we are going through base header. Base header consists of version VER. The content of this 4-bit field defines the version of the IP such as IPv4 or IPv6. If the VER is equal to 6, then version is IPv6. Next is priority. This is 4-bit field defines the priority of the packet which is important in the connection with the traffic congestion. Next is flow label. It is a 24-bit 3 bytes field which is supposed to provide a special handling for a particular flow of data. Next is payload length. The content of this field is 16-bit or 2-byte length field are used to indicate the total length of the IP datagram excluding the base header. That means it gives the length of only payload part of the datagram. Next is next header. It is 8-bit field which defines the header which follows the base header in the datagram. Next is hop limit. Content of this is 8-bit or 1 byte field have a same function as a TTL, that is time to live in the IPv4. Next is source address. This is 16-byte or 128 bits internet address which corresponds to the originator or the source which has produced the datagram. Next is destination address. This is 16-bit or 128-bit internet address which corresponds to the address of final destination of the datagram. But this field will contain the address of the next router and not the final destination if source routing is being used. Next is extension headers. As stated earlier, the length of the base header is 40 bytes and it always remains constant. But in IPv6, the fixed base header can be followed up to 6 extension headers. In IPv4 are optional headers. This gives more functionality to IP datagram. The IPv4 has space for some options field requiring a particular option processing of the packet. These option field are not oftenly used. They can deteriorate router performance because their presence must be checked for each packet. IPv6 replaces this option field by extension header. The IPv6 optional interlayer information is encoded into separate headers that may be placed between the IPv6 header and upper layer header in the packet. These are small numbers of packets, such extension headers. Each identifies a distinct next header value. An IPv6 packet carry up to 0, 1 or more extension header. Each identify the next header field of preceding header. There are 7 kinds of extension headers. Extension headers are not examined or processed by the node along with the packet delivery path until the packet reaches to the node or each of the set of node. In this case of the multicast, identifies the destination address field of the IPv6 header except the hop by hop optional header and the routing header. Therefore, extension header must be processed strictly in order to their appearance in the packet. A receiver must not, for example, scan through a packet looking for the particular kind of extension header and process the header before the processing all proceeding ones. Each extension header has a length equal to the multiple of 64-bit or 8 bytes. A full implementation of IPv6 must include the support for the following extension headers. First is IPv6 header, second is hop by hop option header, third is destination option header, fourth is routing header, fifth is fragment header, sixth is authentication header, seventh is encapsulating security payload header, eighth is destination option header, and ninth is upper layer header. Next is NAT, that is network address translator. The problem that existing the number of IP address is less than the actually required one is practically important. A long-term solution for this problem is that whole internet should be migrated from IPv4 to IPv6. This has begun, but this will take a year to get complete. That means all computers should have IPv6 address instead of IPv4 addresses. A quick solution for this problem is NAT, that is Network Address Translator. It is described in the RFC 3022. The basic idea of NAT is that each company assigned a single IP address or the most of a small number of IP address so as to access the internet. Within the company, every computer gets a unique IP address which is used for the routing the internet traffic of the office. But when the packet goes out of the company and goes to the ISP, the translation of the IP address takes place there. In order to make this scheme work, the ranges of IP address have been declared as a private. The companies can use these addresses internally as per their requirement. However, no packets containing this address is allowed to appear on the internet. There are 3 reserved ranges. First is range 1, 10.0.0.0 to 10.255.255.255 by 8, that is over 16 million hosts. Range 2, 172.16.0.0 to 173.31.255.255 by 12, that is over 10 million hosts. And range 3 is 192.168.0.0 to 198.168.255.255 by 16, that is 65,536 hosts. Generally, most companies choose the address from the first range. Next is mobile IP. A large number of people have a portable computers and they want to work on them wherever they are in the world. Such computers are called as a mobile host. To route a packet to the mobile host, the network has to first find the mobile host. Which mobile models are suitable for mobile communication should be searched first. The networks consist of the WAN, which has the router and host, MANs and LANs. Wireless cells are connected to the WANs. The world is divided into area. Each area has one or more foreign agent. A foreign agent is supposed to keep the track of all mobile users visiting his area. In addition to the foreign agent, each area has a home agent which keeps the track of user whose home is in the area but whose are currently visiting some other area. When a new user enters an area, his computer has to register itself on the foreign agent of that area, and when the user leaves, the area is deregistered should be carrying out. The routing packet of the mobile host takes place by following routing procedure. First, when the packet is to be sent to the mobile user, it is first it to the user homeland. The packet is intercepted by the home agent. The home agent looks for the mobile user current location and finds the address of the corresponding foreign agent. The home agent then encapsulates the packet into payload field and outer packet and sends it to the foreign agent. This is called as a tunneling. The packet is received by the foreign agent who removes the original packet from the payload field and sends it to the mobile user as the data link frame. The home agent tells the senders to send the packet directly to the mobile user. The packets are then routed directly to the user via the foreign agent. Next, mobile IP. Many internet users have portable computers and they want to stay connected to the internet even when they are outside or moving. The existing IP address system cannot work properly for the mobile user. The biggest problem is that addressing scheme itself. So IETF set up a working group to get the solution. The group set to following goal for the solution of this problem. First is each mobile host should be able to use its home IP address when it is anywhere. Second is software changes to the fixed host were not permitted. Next is any changes to the router software and tables were not allowed. Next is most packet for the mobile host should not make detour on their way. And last is no overhead should be incurred when mobile host is at the home. The solution is chosen was one discussed earlier, that is routing for the mobile host. Let us briefly review the principles. First, every site which has to allow the users to roam has to create a home agent. Every site which has a visitor has to create a foreign agent. When a mobile host visits the foreign sites and it contacts the foreign agent there and register itself, the foreign host then contacts the user home agent and gives it a care of address, which is normally foreign agent's own IP address. When a packet is arrived at the user's home LAN, it comes into the some routed attachment to the LAN. The routed then located to host by broadcasting the ARP packet asking the Ethernet address. The home agent answers this question by giving its own Ethernet address. The router then sends the packet to the home agent and it then sends to the packet to the care of address by encapsulating in its payload field of an IP address to the foreign agent. The foreign agent decapsulates and delivers them the data link address of the mobile host. The home agent gives the care of address to the senders so future packets can be tunneled directly to the foreign agent. This solution satisfied all requirements goals mentioned earlier. Thank you.